This is Sam Bushman
and Daniel Morrison
discussing Project MDI, Motion-Driven Interaction. Project MDI utilizes Shawnee State University's face-based motion capture system. The face-based system utilizes uniquely identifiable LED markers strapped to either a suit or a prop. And utilizing a combination of these uniquely identifiable markers and the 32 cameras surrounding the capture space, one can derive absolute 3D positions for each marker.
The goals of Project MDI are to produce a robust API for game and simulation development. We accomplish this by returning only the latest, most up-to-date data while dropping buffered, stale positional data. The existing face-based API has also been wrapped with an easy-to-use collection of C++ classes. We have also worked towards producing interactive demos for university visitors. These demos are easy to set up and are meant for prospective students as well as university business relations. The demos we produce allow for visitors to easily step into and participate in them. Lastly, we aim to gain experience working with a commercial motion capture system.
What you're seeing on the screen right now is the creation of what we call rigids. A rigid is essentially a collection of markers in 3D space that we interpret as a single solid object. As that group or cluster of markers rotates and changes position in 3D space, we derive a single orientation and single central position that represents the collective movement rotation of those markers. Utilizing these rigids, we are then able to create solid objects that we can rotate and move in 3D space in order to create either props or even humanoid models.
This is what we call the Ken doll demo. Using a collection of rigids derived from markers on a human subject, we create a crude doll that illustrates the rigid data in a more recognizable humanoid form.
Similar to the Ken doll demo, we may create a series of rigids for a humanoid model. Using the data from the rigids, we may then calculate angles and positions for forward kinematics. This then allows us to manipulate the skeleton of the humanoid model and translate motions in the motion capture suit in real time to the model.
Using a two-handed prop, we create a virtual camera whose position and orientation mirror motions performed with the prop. Not only able to derive positional data from the system, we are also able to detect the lack of visibility of certain markers. By covering certain markers, we are able to create digital buttons. In this example, we demonstrate the user's ability to zoom in and out the camera just by covering certain markers. Because of the phase space system's fast response time, Such a setup is ideal for applications in VR head-mounted displays, as well as synchronizing virtual data with live action data. In this example, we take a composite shot of Sam sitting in the middle of the room while we pan around him and display the virtual world surrounding him.
As we had stated before, one of the goals of Project MDI was to create a platform to allow developers to easily make games using the face-based system. In order to prove that our API actually works, we felt the need to create a Pong simulation. As we show here, our user is able to take our prop we'd created and move a pedal around in 3D space, bouncing a ball around in the environment. The response time is very rapid and it gives a very fluid feel to gameplay.
Features we currently have in development are inverse kinematics on rigged models.
We also are currently working to utilize the ODE physics library to create a demo that's physics enabled, allowing users to move objects in a live physics enabled environment.
To more encapsulate what data we're getting in, the picture-in-picture live video data and video stream will also be added.
We are also currently integrating a head-mounted display into our virtual camera demo to allow users to see in a real virtual reality environment. Thanks for watching our video. We hope you enjoyed it.